like to welcome everybody to this afternoon session. This is track 3, biogas and landfill gas. The panel today's topic is strategies for removing impurities from biogas to increase the downstream utility. We have four speakers this evening or this afternoon. We will hold questions until the end, if you would please. I'm Tom Abbott. I'm work with USDA, ARS in South Florida at sugarcane breeding station. And we also work with Energy Cane. We have about 4 or 5 products in the pipeline now that just are really outstanding. We're trying to get them to, hopefully we can breed them so we can grow them a little farther north than the Florida border. But our guests this afternoon, our speakers this afternoon, Kirsten Ingvold is a business development manager for Haldor Topso in Denmark. Have Mohammed Farooq, PhD candidate in mechanical engineering, and Pat Carr, is he here? Can he make it in? Hopefully he will make it by the time the presentation's over. Vice President of U.S. Projects and Carbon Clean Solutions. And Joseph, last but not least, but Joseph, our principal engineer for CDM Smith. And I will give them a little quick introduction, and then they will start the presentation. Kristen is business development manager for Haldor Topso in Denmark. He has a background in chemistry from the University of Copenhagen and Technical University of Denmark. He is currently positioned as business development manager in 2012. So I'll turn it over to Kristen and allow him to give his presentation.
Thank you very much. Here we are. Good afternoon, ladies and gentlemen. Today I would like to talk to you about gas conditioning, landfill gas and biogas conditioning. I come from Haldor Topso, and we're a Danish company. Get back to that a little bit later on. But let me just start by talking a little bit about the gas to energy challenge. You see, biogas and then landfill gas, that's basically methane with impurities and diluents. You have sulfur compounds in them. You have hydrogen sulfide and mercaptans, thiols. You also have some siloxane compounds, at least in the landfill gas and sometimes also in the digester gas. And then you have, of course, carbon dioxide, which is a major component. And you can also see oxygen and nitrogen depending on, or various degrees of oxygen and nitrogen depending on your gas. So you can say what we're seeing is that over the last years, the gas streams are becoming increasingly more complex. You also see there is a trend towards realizing or developing renewable gas projects that also requires a significantly higher purity of the gas than you're used to from the the engine space. And you also have, you can say, more stringent off-gas legislations. Now all of this sort of push for more advanced and more complicated gas conditioning and upgrading systems to realize the value of the gas. So, and when it comes to the sulfur compounds, this is actually quite a difficult case, because when you look at what's out there in terms of sulfur recovery technologies and sulfur remediation technologies, you will see that with a lean gas, as this is in terms of sulfur, the concentration levels are more or less too high for cost-effective removal of hydrogen sulfide with absorbents. On the other hand, it's too low for conventional sulfur recovery technologies like Klaus. We also in our company have a process which we call wet sulfuric acid. I think we have more than 500 installations of that all over the world for the power plant sector, where you recover hydrogen sulfide in form of sulfuric acid. But again, I mean, even here you will have some challenges in going lower to say 2% of hydrogen sulfide in the gas. Of course, there is the alternative of having a thermal oxidation, But that requires a high temperature, which leads to NOx formation. You also see that when you have a low heating value gas, there's a large fuel penalty for that. So that brings me on to selective catalytic oxidation. With selective catalytic oxidation, what you do is you oxidize all of the sulfur compounds, and that's mercaptans, thiols, and hydrogen sulfide, also other types of inorganic sulfur. And you oxidize all of that to SO2 in a selective process, so you avoid SO3. Get back to that in a moment. Now, by doing this at a lower temperature than in a conventional combustion, you avoid the NOx formation, and you also avoid the oxidation of the methane. So basically, this is a process where you can oxidize in a methane stream all the sulfur compounds and take them out in a caustic scrubber or other kind of scrubber solution very effectively. So the trick is that when you do this, you really have to pay attention to oxygen level and temperature, because if you have too much oxygen in your gas, you will over-oxidize your sulfur compounds to SO3. That also happens if you have too high temperature. On the other hand, if you have too low temperature or too low levels of oxygen, then you will form free sulfur, and you don't want that either. So the trick is to control your catalytic reaction to be in the sweet spot. And if you do that, then you're actually able to have a very, very selective and very efficient catalytic conversion. Now, we have done many experiments over the last many years with this kind of technology. So we've tested all kinds of sulfur compounds, and basically we have quite good mapping of all the reactions that take place. We are a research and technology organization, so this is what we do, and we do a lot of experimentation and figured all this out. So you basically see that all the sulfur compounds, they are converted into SO2. That also go for carbon disulfide, which is converted to carbonyl sulfide and then on to SO2 as well. Now in this oxidation, you will also oxidize hydrogen and CO to water and carbon dioxide. But when you look at the hydrocarbons, you will not see any oxidation of methane and only a slight to moderate oxidation of the ethane and propane in these mixtures. But higher hydrocarbons than that, these will be converted into to CO2 and CO. So just a few comments about our company. We're a Danish catalyst company. We founded 76 years ago by Dr. Halder Topsoe. We are based in Copenhagen, Denmark. We also have manufacturing assets in the US, in Houston. We also have manufacturing assets in Brazil and China. And we are a very research-oriented company. We spend more than 10% of all our revenue on developing and optimizing all our catalysts and sorbents. Yeah. And we're a Danish company, but we are present all over the world. In the US, as I mentioned, we have our manufacturing assets and sales and engineering office in Houston. We also have a sales representation in Edmonton, in Canada. And then we have a team of top hydrocracking engineers sitting in Orange County and basically doing a lot of process development in the hydrocracking space. Now, our traditional business is that we develop catalysts and sorbents for chemical processing, hydroprocessing, and emissions management. And we also do all the process design and licensing in these areas as well. So for instance, when it comes to ammonia, we basically supply all the technology that's required to convert a natural gas into ammonia for fertilizer. Some of it by license, that's in the urea section of that plant. And the same you can say for methanol. We also supply hydrogen units, or the technology for hydrogen unit, substitute natural gas, and some other areas like sulfuric acid, and we also recently licensed a gasoline unit for a synthetic gasoline unit for a plant in Turkmenistan. Now in the hydroprocessing space, that's our refinery area. We basically can deal with various kinds of refinery stream, do hydroprocessing, and convert into ultra-low sulfur diesel and gasoline. And in the emissions management area, we have technology to take out sulfur. We also have NOx and CO catalysts, volatile organics we can handle, and particulates. Now, the conventional way we do business is that we provide process design packages and engineering packages and licenses. Then we sell catalysts and hardware, and we follow up with technical services and business services for our clients. Now, back a little to the selective catalytic oxidation. We recently realized a project in Iceland, which is related to valorizing a CO2 tail gas stream from a geothermal power plant. So here you have the off gas, which contains CO2 and sulfur and some other compounds. You do the catalytic oxidation, convert all the sulfur to SO2, take that out, and then there's some polishing, and you get food-grade CO2. Now that's interesting in Iceland, because in Iceland you don't have a lot of clean CO2, but you have a need for CO2 for your greenhouses. So in Iceland, they actually import CO2 in canisters. And with this kind of technology, we can supply the local market with food-grade CO2. So that was very, very interesting. And then brings me on to our service that we are entering into the landfill and digester space. Really what we want to do here is we want to take your gas stream, and that can contain sulfur, siloxanes, whatever you have in it, and we basically can design end-to-end a gas conditioning unit and supply, full unit supply of a unit that can deliver a gas that is on spec for what you're interested in. Now, some of the cases we've been working on so far with clients, that has been to take a landfill gas and convert that into a fuel gas free from sulfur and siloxanes for power generation. We've also looked into supplying pipeline quality renewable natural gas for a client. That was in digester space, where you want to also remove the CO2. So basically, take a digester gas and supply a unit that can deliver a purified methane. And then, as I mentioned, we have this project on Iceland where we are comfortable with also taking a CO2 stream and upgrading that to a high value. And a final thing is that, I come from Denmark. In Denmark, we have a very established network for taking the manure, doing an anaerobic digestion, and then taking out the sulfur. And then you're interested in taking out the sulfur also, and sort of keeping the sulfur, closing the sulfur loop so you don't waste the sulfur. And that's also something we can do with our technology. We have designed some systems, and I'll show you an example in a second, where you take the sulfur from your off gas and convert that into sulfuric acid, when you can then inject to your digester and get the benefits of doing that, and avoid having a waste stream also. So a little bit about our service and how we are entering this space. We call this Gecko. This is our gas conditioning service. It's basically an investment-free solution for the client. The idea is that we will use all our expertise in designing as an optimal system, which we then provide all the catalysts and licenses, do all the engineering, installation, and commissioning of the unit. Then our experts back home will do continuous performance monitoring and optimization of the system, and we basically come also and supply and replace all the catalysts required to have a unit that is operating at top performance all the time. We call this no cure, no pay, because there's no upfront investment for the client, and there is only payment basically as long as the delivery gas that we have agreed to is on spec. And as I mentioned, we have all the sorbents, all the catalysts, all the capabilities in terms of process design from other areas also to go in and supply the full units. So that's what we want to do. And basically for the client perspective, there will be some site preparation. Typically that's done also, that has been done earlier, but there will be some modifications maybe. Then there's handling of all the utilities and consumables. And then there will be the on-site operation and maintenance of the unit. But all the difficult stuff, we can handle that from our remote. So just to wrap up a little bit before we go into some examples. this solution where based on the sulfur oxidation, that's very ideal for methane gas streams where you have the sulfur in it, because you don't have any oxidation of the methane. You have a very, very high conversion, very high selectivity, not the least, to SO2, and you don't have any NOx formation. And these are simple and modular installations. They are compact, they're easy to operate, and we can basically configure to take out also siloxanes. We can also configure to take out nitrogen, oxygen, and if you have other impurities, we're ready to take a look at that as well. Now, I have two examples here. I mean, we can easily develop some other examples. I've just taken two examples that we have developed for clients. And one is for a biogas plant, where you take the raw gas, then in this configuration there's an amine wash to take out, you can say, the methane. Then there is a drying and compression afterwards. That was not in our scope at this project. And then the off gas, which is basically CO2 and SO2, hydrogen sulfide, that goes into a heat exchanger, where you heat it is heated with the effluent from the reaction, the oxidation reaction. Then the product gas or the exit gas go into a scrubber, and in this case this was a hydrogen peroxide scrubber where you take out your sulfur compounds as sulfuric acid, and then the off gas is essentially free from sulfur. So this is a method, you can say, where you take in an anaerobic digester gas, convert that into high quality methane, have an off gas that is clean and meets all kinds of environmental legislations, and you also close the loop in terms of the sulfur. Now, the other example I have for you today, this is for a landfill gas. Here you don't have so high concentration of sulfur compounds that the reaction is self-sustaining in terms of the energy supply. So we had to add a trim heater in this case. But on the other hand, here you have high siloxane content, so we needed to take that out as well. So in this configuration, you have a siloxane absorber and the oxidation catalyst, and then you take out the sulfur compounds, the SO2, in a caustic scrubber. And in this way, you get you can say a clean gas, which is very good for your gas engine, because there is no sulfur and siloxane in that. Now, I guess the take-home message for you guys today, and you're more than welcome to come and talk to me, and we can talk in more details about your specific gas stream. But the message is that we are entering now this market with a gas conditioning service solution. So it's not like a product sale, it's a service solution. And we see this as being an interesting option in the whole landfill and digester gas to energy space, particularly because it's de-risking significantly because there's no risk with the technology. We assume that risk. So that was basically what I had for you today. You are more than welcome to come see me and we can talk more about it. Or if you want, we can get in touch on email. Feel free to give me a call, or you can visit our website. Thank you very much.
Thank you, Kirsten. Next speaker is Mohammed Farooq. He's a PhD scholar in mechanical engineering at, is that Harriet?
It's Heriot-Watt University.
Heriot-Watt, thank you. University of the United Kingdom. He's working on regenerative activated carbon adsorption for low biomethane production. I'm a little out of my field on this, if you haven't guessed already.
Okay, I will explain.
He's authored several research papers, so at this time, please, Mohammed, if you would please
Yes,
go ahead and give me the presentation.
Hi everybody, good afternoon. My name is, as he told you, Mohammed Farooq. I'm doing PhD in mechanical engineering. So basically my PhD is about the purification of biogas for the production of biomethane, and I'm using the physical adsorption system, and I'm using the activated carbon for the physical adsorption. just my supervisors, John Emerson. I'm like a student, so just write down in the form of a paper. So, well, this is track 3. So, yeah, so this will be the outline of my today presentation. So it will be introduction. I have experimental setup. So I actually built my reactor during my first year of my PhD. Then we have some result and discussion. I'm still working on my results. So like I just finished my second year of my PhD, and I'm just like kind of like doing my experiments by repeating with with varying parameters for getting some good results. And then we have some conclusion, acknowledgement, and the references. So, well, because I'm like working in the UK, so my main objective is for the production of biomethane for the UK natural gas grid. So, like, it's a very good carbon neutral fuel, it's a biogas. And the main UK barrier is actually to get the low cost biomethane for the injection in the natural grid, because like there are a lot of conventional methods and a lot of industries who are producing the biogas, and still like there is a potential to replace up to 50% of the UK natural gas need with the biogas. So the typical biogas composition, like around 50 to 65% methane, and similarly 30 to 45% CO2, and like H2S concentration varies from 1000 ppm to 1%. So basically it depends that what kind of input resources like you are using. Is it animal dung, landfill, or the food waste material, or whatever like you are using. So basically I am actually, because I told you that I have built a reactor and I'm using the gases, like I have buy some gas cylinders, and I like made a biogas in my reactor. So the UK government is like very much interested in these kind of projects for getting the renewable energy into this, and they provide the renewable heat incentives. Like there are different schemes. Like if you have 250 megawatt biogas plant, and then if you have 500 megawatt plant and higher, then they give you more incentive. Like there are a lot of figures available in the literature as well. So. And this particular RHI scheme, they started after 2011. So they are like very much interested to the people, like, and especially the strong political drive towards the production of biomethane from the UK government as well. So this is a kind of like we have a lot of conventional methods which are available. So there are absorption, adsorption, permeation, and like, so we have like the water washing system, which is a very conventional system as well, and we have some chemical absorption, we have adsorption, we have cryogenic methods. And on the right side, I have made a little comparison of different parameters, which is also from literature again, like to just compare my method with the other methods in like as comparison with the low cost production of biomethane. So this is my like experimental setup. I have like CO2 gas cylinder, the nitrogen we have in the lab, and similarly I buy a special gas cylinder for nitrogen mixed with the 99% nitrogen and 1% like 10,000 ppm of hydrogen sulfide. So my main focus is basically on the removal of H2S, because like there is no much methods available, like cost-effective methods available in the literature for the removal of H2S from biogas to produce biomethane. So I'm not using any methane actually. We are just considering like I'm using the nitrogen, because I'm working in the lab scale, and safety is a big issue. Like if you are working in the lab, like so like we are just running with the nitrogen, and I have 3 different samples of activated carbon, which are like the commercial activated carbon provided by a company. And I have like different flow meters, so I vary the flow rates. And then like I have built actually my reactor, so which is this one, which is the regenerative activated carbon. And I have just like put the glass wool and the filter paper on the top and bottom side, just to avoid the activated carbon to flow down. And then I have the mass spectrometer to measure the gases actually. and which is attached with the computer system, and we have a mass soft. So this is a kind of like my experimental setup, and you can see the thermocouples on the top and bottom side. I will tell you later on what's the purpose of these thermocouples actually. So like I did some material characterizations, so I need to do different analysis to get like how much is the carbon content and how much is the ash, so that I can know about the actual adsorption capacity of the activated carbon of my different samples. So the 3 samples which I am using are like different in structure as well. So one is the granular activated carbon, and the second one is in the pellet shapes, and third one is the powder shapes. So like I have selected different kind of structure of the activated carbon, so that like definitely they have different adsorption capacities as well. I will show you later. So to get some good results, and I can do my PhD as well. So these are like different like carbon, hydrogen, nitrogen, and ash content and oxygen. I did some like ash analysis, proximate analysis, and elemental analysis. And similarly, I did like BET analysis for the surface area calculation, which I have shown in this slide. So this is just showing the all the 3 materials. I given name them AC1, 2, and 3. It is showing the relative pressure and the absorption of like these are these basically nitrogen isotherm for the surface area calculation. Then I have actually determined the adsorption capacity of my activated carbon. So in our lab, like we have a facility of like a thermogalvanic analyzer, which is we call as TGA. So I did actually my adsorption analysis on some particular machine, and then I calculate the adsorption capacity of my all samples, and then I compare the same analysis on my own rig, which I have shown you in the previous slides. So just to compare that, okay, the adsorption capacity, like my rig accuracy can be determined from the standard method as well. So this is a standard method, like I have done like on 3 different temperatures, like 25, 50, and 75 degree, because basically, biogas production is from anaerobic digestion. So anaerobic digestion, like the temperature is roughly like roughly from 35 to 50 degree range. So I have selected 3 different kind of temperature to calculate the adsorption capacity. And this is shown on the right side of the figure as well. So this is actually the breakthrough capacity of the activated carbon adsorption from my experimental rig, and you can see that like the adsorption time is roughly like 10 to 12 minutes. Well, it also depends on how much activated carbon, how much is the weight by weight percentage you are putting in the reactor, and what is the flow rate of your gases like you are passing through. So, but eventually we have like adsorption time, and then we have to dissolve the gases. Like I am using the nitrogen gas for the desorption. So like we have long desorption time. So this is actually the second phase of my PhD as well. So the first phase is for the adsorption of biogas, like to produce biomethane, and second phase is to reduce the desorption time as well. Because if we have 10 minutes of adsorption time, and we need like 1.5 hour or 1 to 1.5 hour for the desorption. So like if in some industrial setup we have 1 vessel for the adsorption, then maybe we need like 7 to 8 or 7 to 10 desorption vessels at a time, like to make the adsorption and desorption analysis on the same time. Otherwise, if we have 1 to 1, then there is a long time for the desorption. We have to wait, and definitely that is not the cost effective. So this is just a comparison I have shown over here for my rig with the TGA, which is the standard method I did for the adsorption analysis as well. So like I got roughly similar, which is, you can see that I have just shown the one sample over here, which is 5.48%, and then we have like 5.6 as well. So it's quite similar, because like definitely I have like built my own reactor, so there are some chances that there is a little bit inaccuracies in that one, because I did everything myself during my first year of my PhD. So So this is actually the desorption of activated carbon. So, well, there are a lot of methods available for the regeneration as well and for the desorption, but they are very expensive. Like people are using the microwave regeneration and like the thermal regeneration with the high pressure and temperature as well. So what I am doing actually, what we did, we supply a very low voltage like throughout my reactor. I have shown you in the start the thermocouples over there. So I have attached my reactor with the thermocouples and supplying the very low voltage system. Like I tried with the 10, 20 and 30 volts. And like first I run with the without voltage system. And you can see like we got here like it's about 120 minutes or something like that. And then when we are giving like the 10 volts and here are 20 volts. So basically the time is reducing. Like this we were expecting, and if we keep on doing this, like if we increase our voltage, like in our normal supplies we have 220 or 240 volts. So it's our prediction on these low voltage analysis, but I'm not sure because like I'm running all these gases, I'm measuring these gases with the mass spectrometer, which is highly not recommended to run with some other high voltage like the normal voltage system as well, because that will disturb the inside circuit mechanism. So I just run through the low voltage system up to 30 volts, and like my university also don't allow me, but we're still trying to figure out this issue, because we want to know that if we increase the voltage, what will be the effects on these activated carbons, and how the desorption time we can reduce. And this is for this method we don't need any extra cost. I have already I sent one of my journal paper in a journal, and that's under review, and hopefully I will get some good results there. So basically in first phase I did the adsorption, and first I did the adsorption with the conventional method which are available in the literature as well, and then I compare with the water washing. Water washing is the most commonly used method for the biogas purification, but definitely every method has some advantages and disadvantages. And the good thing with the activated carbon is it's very cheap, and it has good surface area, and it has a good adsorption properties as well. So, and similarly for the desorption, we are just trying with the low voltage system, and we predict that as the curve I am getting quite similar straight line. So if we keep increasing the voltage, let's say up to 220 volts or 240 volts, so hopefully we will get the desorption time reduced from 120 minutes to 15 minutes. So according to this graph, but still I'm repeating my experiments, and I need to figure out for my PhD stuff and to get my research published as well. So this is all about my presentation, and then we have some conclusion on the basis of this one. So this is the economically viable biomethane production from biogas, and which results in the lower capital and operating cost, and therefore higher overall profit. So I did actually some software, not me, I did actually one of my colleague. So she's doing I did the experimental stuff, and she's doing the simulation stuff on the high seas and Aspen software analysis. Maybe if someone's background is from chemical, they probably know. And but I didn't present that over here because that's not my data. So, and this is very safe and environmental friendly, and results are low or methane losses, because we are not using any chemical, we are not using anything dangerous. So, and it's environmental friendly as well, because the most of the methods for the removal of H2S is a bit tricky, because that's toxic in nature. And well, from the simulation analysis, we figure out that we can replace it up to 20% of the OPEX of the biogas to biomethane production, and it's a guide for the design and operation of the industrial system. And one of my other colleague, he will be doing some other modeling of my experimental results. So like we are working in a group. Our group is actually the carbon capture storage group at the Harvard University. Is a very renowned group as well. Well, I'm also the part of, because I'm also capturing the carbon dioxide as well. So yeah. So I am really thankful to my institute who actually provided me the funding to travel all the way from UK to US to attend this conference. And my special thanks to the conference organizing committee who like cooperated with me all the time for getting any kind of letter for the visa or stuff like that. And I'm also thankful to the University of Engineering and Technology, Lahore, Pakistan, for providing me the funding for conducting my PhD research. I'm funded from my, like halfway funded from my government and halfway funded from my university in the UK. So that's why I'm like getting these opportunities. So if you have any questions, we can have any discussion after the session. And thank you very much. Thank you.
Did Dr. Patkar make it in? Okay, well, we'll move on, and we'll have, then our next presenter is Joseph Farooq. He's principal engineer and for senior solid waste engineering and landfill and gas in Boston, Massachusetts for CDM Smith. Has over 40 years experience in solid waste projects, and over that 40 years has developed a number of innovative landfill and across the United States for handling landfill gases and what have you. So, Mr. Kuro, if you would please.
Thank you. Good afternoon. Good to see everyone here. Hopefully not like the last session that someone fell asleep, and I won't call them out on that, Steve. I see that you're awake now. Okay. That's not me.
Just skip on past that. We want to go on to the last presentation.
There we go. Okay, so I want to talk about desiccants. The little things look like marshmallows and don't taste like marshmallows, but we'll get into some pictures of them. I want to talk about a fairly simple system to remove saturated water vapor from landfill gas. No moving parts, just sits there and works. You turn it on, you turn it off, and the word that everyone in this country likes to hear is it's pretty cheap. You can treat low landfill gas flow rates. Most of the equipment available is in a larger size than this. We can go down to about 1.5 SCFM if we need to. Typically, it'll run in the 200 to 400, maybe 500 SCFM range. You know, it's a way to treat gas that's, you know, where anything else might be not cost effective. It's an alternative to flaring. It can be a supplement to a flare. Very flexible. Switch back and forth, turn the thing on. Like I said, turn it on, turn it off. You don't need a 24/7, 365 operating schedule. You can run a few hours today, you know, a few days next week, and run it in the winter, shut it off in the summer, you know, that type of operation. Maintenance, you pull the top off, fill it up with desiccant, put the top back on, and you're back in business again. Then you go home. Don't need to keep an eye on it. And like I said, no moving parts. We have a blower, and it supplies, pressurizes the gas to the system from there on through, no moving parts. Can be a typical system can be either a single or dual desiccant. The first one gets you down to about 40-degree dew point, and the second would get you to 20-degree, depending what you need. You may just use a single. There's just tanks full of desiccant, and we'll look at some pictures. The one that I want to run through is a heating system, and they refill the desiccant at the beginning of the heating season. They run for about 6 months, and close it up, shut it down, bottle it up, and then next heating season, refill it again and run. So it can sit for many months at a time with no attention at all. It just, you shut things off, close the valves, and walk away. Basically what it does is it takes the moisture in the landfill gas. The desiccant is basically salt tablets, so now I've let the secrets out. The salt absorbs the water, and you have salty water coming out the bottom of the tanks. Oops, come on. Okay. This is a basic system. This is a two-stage system. The gas comes in here. This one happens to have 3 blowers. We don't do that anymore. The problem was that early on we had trouble with the blowers, so it was decided, well, if 1 is good, 2 is better, we might as well put in a 3rd. So we come through the blowers. Problems we had with the blowers were things like explosions. You know, in the middle of the night, the blower would just explode. Still never found out why, but we have eliminated that problem. We go through, whoops, not that way. The laser is that button. Okay, so we go from the blowers, pressurize the gas. This system runs at about 20 psi. Pressurize the gas and go through a pre-cooler. And what that basically does is take the heat of compression out of the gas, so it cools it down to ambient temperature. Go through a separator where you can see it right here. It's basically a cyclonic separator where the water droplets are removed from the gas stream. So that's kind of a coarse separation. And then the gas flows into the 2 vessels. So you can see it comes down through the bottom, up, sorry, into the bottom of the vessel, up through the salt bed, out the top, back down, up through the second one. We have bypass valves, so you can use just 1 vessel if need be. If you do run it in the wintertime, you don't need to reduce the dew point a lot because the gas comes in cooler. You just use 1 vessel, so you can get you can reduce the dew point by 20 degrees in 1 vessel and 60 degrees in the second. So from the vessels, we go through a second knockout that any water carryover we knock out here, and basically we have dry gas that goes out into the pipeline. Also, I forgot to mention with this last separator, it does 2 things. It knocks out the liquid, and we get some siloxane formation, although if we do, it usually gets washed out with the salty water. But if we do have any dust carryover, depending on the conditions, we'll use a 10, a 1, or we're just trying now a 0.3 micron filter in this separator, just to catch any. You know, this is not for super sensitive applications. Basically, this is for a heating system. So, we've seen this one before. So the gas comes in right here. So there's a flare outside of this building. The gas comes up. When we're not using the system, gas goes to the flare. So it comes through here, and we have, in this particular one, we have 2 blowers. So we split to the 2 blowers and pressurize the gas to go through the system. Or we can use one side or the other and just use 1 blower depending on the flow. Everything in the system is either stainless steel or, as we prefer, since it's a lot cheaper, high-density polyethylene piping and plastic valves. We get, sometimes the plastic valves being PVC are a little bit susceptible to damage. We've had a couple that have been hit and broken, but these actually sit behind the vessels, so you got to try pretty hard to break them. The HDPE piping, you know, you can pretty much run it over with a truck, and it deforms a little bit and snaps back, so not too bad. This particular one is inside a building because it's in an area that it isn't really a cold freezing weather. It's in Virginia, so the first one we did was outdoors, and they did have a couple of freeze-ups, so this one was put in indoors with actually minimal amount of heating. There are compressors, or a compressor. to give you a little scale, that compressor is about the size of a shoebox. Not very big. It's a 400 CFM compressor. I'm sorry, that's a 200 CFM compressor. We don't use that type. We don't like to use this type anymore because of a couple of things that parts availability is impossible. They're not repairable. They're basically throwaway units, but, you know, being the size of a shoebox, they're not all that expensive, so, you know, we keep on using them. Motor has a, oh, come on. The motor has a variable frequency drive on it, so we can vary the speed of the compressor to match the flow rate needed for the system. The gas comes in to the compressor through the top, discharges the bottom, and goes over to the vessels. We don't, in earlier versions, we used to use the butterfly valves for throttling. And, you know, if you know butterfly valves, they don't throttle very well. So we went with the variable frequency drives. You know, with the price of the VFDs coming down so much in the last few years, you know, it's a commodity now. And that's like a 5 horsepower motor. So, you know, we don't need to spend a lot of money for the VFDs, and it throttles a lot better than the throttling valves. Flow meter, you know, to meter the gas through the system. In this case, that is the billing flow meter, so that the gas is treated here. This particular one goes to a heating system, like I mentioned, and I'll show that heating system in a minute. Just a bunch of piping, valves, the components of the flow meter. Yeah, pretty straightforward stuff. Okay, so once it gets through the flow meter, we get into the aftercooler, where I said that, you know, any heat of compression is dissipated here, so we don't need to consume desiccants to do this first stage of cooling. You do get some water droplets that come over, and this does a good job. I'm sorry, as it cools the gas, we get water droplet formation, and that gets removed in this. So just a little cyclonic filter, the water drops out the bottom. Pretty simple. It goes to the condensate system at the landfill. So one of the things I want to point out here is right here you can see these buckets. The two different kinds of desiccants. The first stage is you know, kind of plain old salt. It comes in paper bags. You just want to store it indoors so it doesn't get wet. The second stage, if you leave that bucket open, in about 2 weeks the bucket will be pretty much empty. It'll absorb so much water and just dissolve itself. So you had the first stage you don't have to be that careful with. The second stage, you're going to lose it if you don't use it. Okay, so from there we go into the bottom of the vessels through these valves. We can isolate. There's all kinds of isolation valves. You know, the plastic valves aren't all that expensive. We can set it up so that we can come through this pipe up into the vessel, out the top, and then down into the next one. We can isolate and flow through just one vessel, or, you know, if need be, we can just bypass and flow through none of the vessels. So if you run out of desiccant, it's got a little sight glass on the side. If you should run out of desiccant during the year, you just bypass that vessel, pop the top off, fill it up again, and put it back online. You know, as quick as you can put the stuff in is as quick as you can be back online. And you can see here, this is the hatch on the top, so there's a little platform. You get up there, pull the hatch off, dump the bags in until it's full, and there's no set amount to put in, just dump them in until it's full. Put the hatch back on, adjust the valving, and you're back in business. Now this first stage, that one will reduce the dew point by 20 degrees, so if you have 100-degree gas, it'll reduce the dew point to 80. Maybe, whoops. Okay, this is what the stuff looks like. Like I said, it looks like marshmallows. They're hard. It's salt tablets. Nothing magic about them, just little round salt tablets. So kind of similar to water softening. So again, you just dump these out of the bag. Both stages look the same. They react a little different. The density is a little different. So you need to keep them separate and, you know, keep track of which ones you have, because the second stage ones are about 4 times the cost of the first stage, which still isn't all that much money, but, you know, you don't want to waste it. So then we go on to the second stage. This is the trade name for the stuff that's inside. Same as exactly the same vessel as the first, the same hatch up on the top. You get up there, dump the stuff in. You don't need to wait until it's empty. You can fill it when it's half empty, or whenever you feel like. Really, you don't want to run it out. Obviously, it won't do any treatment anymore. And there is a minimum depth. I believe it's about 18 inches that you want to maintain. So that system was in a building, couldn't see much of it. So here's a system that we did outdoors. The two vessels, the piping coming in. It's a little bit different setup. Comes in, the bed of desiccants in here. Comes out, back down to the second one through. This one didn't have as much valving on it as the previous one. They wanted to use both at the same time, so we really didn't make any provisions to separate them. So we have 5 minutes left and running right on schedule. Okay. So the gas, after it gets through, it gets dehydrated to whatever level you want. It comes across, and you can see the gas from the first system that we looked at runs about 10,000 feet, almost 2 miles, and basically across a parking lot into this building. This building is a bus maintenance facility in Virginia. They have about 1,000 buses. They do bus washing and maintenance. So this is the heating system for the building. Although, this is the landfill gas coming in. You can see before you go into any building, we have a final filter, and then natural gas coming in. So this facility has been in operation for about 5 years now. If you look real close, you can see the natural gas valve isn't even open. They've never used natural gas in the system. So, the gas is nice and clean, dry, comes through here into the building. So, if I can, where does it go? It goes to these little babies. This is a standard radiant tube heater, if you're familiar with Home Depot. If you walk into most Home Depots in areas where they need heat, you'll see these hanging from the ceiling. It's kind of the Home Depot standard. They don't sell them, they just use them. So the gas comes into the building through this pipe into this ignition chamber, and then you have a stainless steel tube, and some of these can run 50 feet long. You can't see it that great, but it has a stainless steel hood over it so that it's polished stainless steel. So you have the radiant tube creating the heat, and the stainless steel does two things. It reflects the heat into the building, and it prevents the heat from going up and overheating the roof. So that thing just sits there. There's no real burner on it. The gas comes in. There's an ignition, basically a spark plug in here, and a gas valve that regulates the flow of gas and the heat into the chamber. It doesn't need any pressurization of the gas because the gas is already pressurized before it gets into the desiccant system. So it's delivered here at about 10 to 15 psi, and it just fires down the tube. Each one of these burners is individually controlled. You can see that they have a whole bunch of them. There's one there, one there, one there. You can see the gas lines coming into the combustion chamber and then down the tubes. This is bus washers. So we do have gas coming down to the right side here. There's a water heater that uses landfill gas. All these burners are standard burners. The nozzle's been changed. The orifice plate's been changed to accommodate landfill gas. They work fine. At the beginning of the season, they clean the igniter, the flame rod, and the orifice plate, and they run usually all winter. There's the business end of it. That's what's inside the little combustion box. You can see air intake here. The gas comes in one of these pipes into the igniter. They have your combustion controls, your fuel valve. Actually, the igniter here, this is the igniter control, the actual igniter and temperature monitor right here, into the combustion chamber and then down the tube. Every one of the burners, the heaters has its own thermostat, so you can have control in different parts of the building. Once the gas gets into the burners and it starts burning, the heaters don't act any different than if they were fired by natural gas. It's all calibrated for landfill gas. You tell the thermostat that you want whatever temperature you want, and it maintains it. It's nice and toasty warm in there. So you're working on a big old bus that just came in out of the cold, and you get nice and warmed up. Okay, so applications, obviously this garage, storage facilities, maintenance facilities. We have the bus wash, and the reason we have the bus wash, or one of the reasons, is that's our heat sink. So when we have days we might have too much gas, we actually overheat the bus wash. So you can hatch chickens in there, it's so hot and humid sometimes. Thing turns on and off. I mean, you start the blower up, open your valves, and make your adjustments, if any, and you're running. It's instant. Like I said, flows down to 1.5 CFM up to 3,500 if you put parallel units. Each set you can get a set of the 2 tanks that's about 1,000 CFM total. And it's dependable and totally unattended. Nobody ever goes out into that building until it's time to shut it off or turn it on. It is monitored, computer monitored, but we don't need someone out there all the time. Capital and O&M costs, it can be comparable to a flare, usually lower. So, it's very flexible. It doesn't have to be used for heat. You can have some kind of process. We're looking at a system right now for a brick kiln, and they'll use around 1,000 CFM. We have a double unit for that. They'll turn it on when they need to cook bricks, and when they finish cooking the bricks, they'll shut it off. The desiccants, easy to store. They're salt tablets. You could eat them if you wanted to. Salt isn't my thing. I'm on a restricted salt diet, I guess. They're not hazardous. Like I said, unattended operation. Now, capital costs, when the system's not operating, there's absolutely no maintenance cost. You button it up and it sits there. Unless something hits it or something happens to it, it's ready to start up when you're ready to start it up. It doesn't need anything. As far as costs go, and I'm over time by a minute, the system that we saw was about $50,000. A comparable flare system would be about $250,000. And for a gas conditioning cleanup system for that size flow, we just priced one. It was, actually a little bit larger flow. It was $1.5 million. So one for this size would be about $1 million. So if you need really, really clean gas, it's $1 million. If you can go to just really clean gas, it's 50 grand. So it's a pretty good system. We have a few in operation now, mainly on the maintenance facilities and mainly for cyclical operation. But we've got a whole bunch more coming down the pipe. Thank you.
All right, Dr. Patkar, we are missing one speaker, so we have a little extra time. So if you have questions, please shout them out, put up a hand, whatever. Any of these panelists will be more than glad to offer a educated guess. Anybody? Yes, sir. Go ahead.
How do you address the safety concerns, or how do you see the flammable safety concern of applying a voltage to a carbon source with flammable gas?
Yeah, so as I told you earlier, that is actually our concern as well. So we just apply 30 volts, and we consult with our electrical workshop center as well. So up to 50 volts, it's okay. It doesn't disturb the system actually. But if you try to use a higher voltage, it may also it also because H2S is again the toxic. But H2S may not be more concerned with by applying the voltage system, because I apply 30 volts and there is nothing wrong with the H2S even. But we are more concerned with the mass spectrometer, the gas analyzer actually which are using, and that's again very expensive as well. I think so 60,000 pounds UK pound. So that's actually stopping us to increase the voltage system. So that's still the major concern. But up to 30 volts, we are not getting any kind of problems. And we did some testing, our electrical workshop guys, and up to 50 volts as well. But they didn't recommend as well, the same issue we are still like having same kind of like definitely if we want to increase the voltage, that will be a problem. But we could not still get out of that.
Any other questions? Yes.
So Joe, is your system, it's just taking water out? Yes. It's not taking any other way?
No, it's just for dehydration, so it's not a system that would be used on gas that would have high hydrogen sulfide, for instance.
Anyone else? Yes, there.
This is a question for Preston. You had put up a slide that showed the slot snake absorber.
Yeah.
What kind of media or mechanism is being employed in that absorber?
Well, that's one of our, you can say, it's not a catalyst. It's an alumina-based system. We have that for we do that in other areas as well. So it's a commercial product we have, and we have many installations in other areas, just not in landfill gas.
Anyone else? Yes, one in the back. Yes, sir.
Joe, I see you had trade names on those different desiccants. There's nothing proprietary about them?
Nope. I have the catalog here if you want to buy some. I'm not selling them. We just do the system. They won't do the system design. They'll say the vessels. So what we did is design the entire system, and we also do the work at the landfill, putting in the wells, getting the gas to and sending it out.
Have you generated any curves to show with incoming moisture content the flow rates that a certain vessel will be able to accommodate?
Those are actually in their catalog. To let out another secret, it's basically a compressed air dryer that's been modified a bit to handle landfill gas. There's some coatings inside the tanks and a few special features, but there's no magic. I wish there was, but there isn't.
Yes, sir, in the back.
Yeah, talk about permitting modification. You get challenges there?
Well, the site already has a permit, and the site would need a permit for a landfill gas flare. So as part of that permitting, you send the gas off-site, and the off-site use needs a permit to burn the gas anyhow, even if they were using natural gas. The permitting with this particular agency, we've done this in Florida, especially in Florida. It's, put those few lines on the permit that says what we're doing, and it really doesn't do anything to the gas, so it doesn't really change it. It just dries it so that the emissions don't change. Right. So, but the destruction efficiency in the flare is set at the 98% for an open flare, and the destruction efficiency in the burners is assumed by the agencies to be also 98%.
I had a question here up front. No?
For Joe. What is your salt usage for CFM approximately?
Good question. Running at 400 CFM through the winter, we use about half of each vessel, which each vessel holds, these are 500 pounds. So we use 200 to 300 pounds in each vessel per year. The first vessel costs about $2 a pound. The second vessel, it's about $6 or $8 a pound. So it's not a huge consumption of desiccant.
Yes, sir.
What's the difference between the two types of salts that you have? Second one is
I knew someone would ask that question. I really don't know. And they look exactly the same. One just sucks up moisture faster than the other. It's a proprietary to the manufacturer. I'm not sure exactly what they do to the salt to make one better than the other. But like I said, if you're holding two of them, one of each, they don't look any different.
Calcium chloride do you, second stage?
I've asked, they don't tell.
Yes, sir.
Mohammed, are you working with a special activated carbon? Like, is it activated for H2S or is it just activated?
Well, I am using 3 different samples as I told you. So one of them is a Darko H2S, which is like, all are basically commercial activated carbon. So one of them is like the company called the Norit activated carbon. So I just got from them just free samples for doing my PhD. Like I need a half a kilo of one sample. So the first sample is the Darko H2S, which they define that this is well renowned for the H2S removal. And if you visit their website, they have like shown that is a good absorption capacity for the H2S removal, and like they have shown some other curves and make some comparison as well.
Yes.
Yeah, just a few questions, Mohammed. First of all, you're removing H2S under pressure or atmospheric pressure?
Atmospheric pressure.
Atmospheric?
Yeah.
And what kind of removal efficiencies have you noticed? I might have missed it.
Well, I told you like I'm in second year of my PhD, so I have not like done all the calculation till, because like I need to make some comparison. So I'm doing my experiments, right? And like I'm calculating the absorption capacities. So like maybe by this summer I will be doing all the stuff.
Right.
Yeah.
Now,
So.
why would you, in our company, we looked at generation of carbon, activated carbon using direct heating via electrical heating, which is what you do in resistance heating.
Mhm.
Why did you choose that method over just preheating the regeneration gas with an electrical heater running hot through it? Because you don't get uniform heating of carbon when you do direct resistive heating. Any reason why you chose to do it that way?
Like why I have chosen the activated carbon as a
No, to heat it with electrical heating as opposed to just heating a media to like a gas or
yeah, but I'm not like I'm doing it on the atmospheric condition, like the normal temperature and pressure.
Okay, well, let me see if I understand. I understand the absorption part.
Okay.
Okay, atmospheric.
Mhm.
Then after the carbon gets saturated, you're generating it with methane that's been heated indirectly, passing through the carbon, which the carbon is being resistively heated. Is that the way you're doing it?
Well, I'm putting a low voltage as I told you. Well, maybe I don't understand what
But you
you.
put low voltage, I understand, but you're using the carbon is being heated by.
Yeah.
So resistance.
Yeah,
I'm
exactly.
saying it would be easier just to put an electric heater on the regeneration gas.
Yeah.
Get that temperature.
So like this is we called it a microwave regeneration as well,
Okay.
right? But like still for microwave regeneration, we need like high temperature. That's done like under 700 to 800 degrees Celsius.
Right.
So like we need some kind of resource for providing the high temperature, right? Which will be adding in the cost of the process as well. So like one of my colleague is doing the microwave regeneration with the same procedure, right? So well he's doing with the different with different other parameters, but still like we can do like there are a lot of regeneration methods as well. But well I'm working for the low cost biomethane production, so that's why I have chosen this one, because it doesn't require any cost. Yeah, just the guy question like for the voltage system, we still have some problems with the high volts.
Another fundamental question would be, I mean, you regenerate the carbon, you get the H2S out. What do you do with it?
With the H2S,
I'm sorry?
what I will do with the H2S, which I will remove.
Well, you're using methane to remove the H2S as a regeneration media, so you're going to have methane
Yeah.
exhausting with H2S. What was your plan on doing that in a commercial?
No, well, because my PhD is about like the biomethane production. It can be done like someone else can do those kind of experiment, but I am focused just for my PhD, not for the commercial stuff, because I have built my lab scale reactor, so I'm more concerned about my PhD degree, yeah, at the moment.
Do we have any other questions? Maybe you guys can continue this on if after the meeting. We're probably getting into wrap-up time. If there's any other questions, we do have another one coming in. I know we had a little extra time, but if anyone has another question, please. Yes, sir. Go ahead.
In the gecko system, is there a minimum scale that you're,
Say again.
are you targeting your system towards or your service towards a minimum scale plant?
I mean, we haven't really worked out a minimum scale yet. So far, we have even smaller scales. I think the smallest we have been looking into have maybe been like 1,000 normal cubic meters per hour. What's that? Like 600 SCFM, something like that. But I'm not saying we cannot go lower. I'm just saying that's the limit we have had so far. And that was for a digest upgrading system.
Anyone else, or have we beaten this to death? Well, if there's no more questions, these gentlemen are here. You're more than glad to speak with them after Kirsten is down. I think.
Sorry?
Do you have a display downstairs or no?
No, we don't have a display,
Yeah, okay.
but I have some leaflets I'm happy to pass on to
There you go.
Just strike me out and we can have a talk.
So I guess we'll conclude that for this session. Thank you all very much for your attendance.